Now that we've looked at probability and all of the rules and the concepts surrounding probability, especially taking a strong look at what we learned in Module 9 about the central limit theorem, it's now time for us to take a look at how samples from a population can be used to infer information about an unknown population parameter. Specifically in this module, we're going to look at building confidence intervals about populations when sigma, or the standard deviation, is known. So the purpose of statistics is for us to find out information about population parameters. Population parameter is, we define as being a statistic that's calculated from a population. Usually this value is unknown. The population is too large enough or it's too elusive enough for us to really know or to be able to find out what the number is that represents the population number. Samples are what we turn to in this respect. Samples can actually tell us a lot of information about a population. When a value from a sample is used to estimate a population parameter, we call that value a point estimate. Symbolically even, we differentiate between the two. We use X bar. You've seen that frequently used as a symbol for the mean of a population, or the mean. But we would use this, because this represents the mean of a sample, as a point estimate for the unknown population mu, which is the mean of the population. Statistical inference is methods from which we can draw conclusions about the larger population based on what we look at from sample data. And in this particular section, we're actually going to sort of narrow down and simplify the processes and the conditions under which we're working. Many of these conditions are unrealistic. However, this will provide us a framework in which we're going to look at the process itself of taking samples from populations. Three big assumptions we're making. Number one is that the sample that we pulled from the population is a simple random sample, and that we don't have any problems collecting that, and that it's very representative of the overall population. When we looked at sampling techniques, we saw that this is not an easy thing to do. But for this section, we're just going to assume that the sample we get is a good representative sample. Secondly, the variable that we're measuring about our population has an exact normal distribution within the population. And then third, we don't know what the population mean is, but we do somehow know the population standard deviation is sigma. This, of course, is the biggest assumption that we're making. Normally, we have no idea what sigma is because we have no idea what mu is. If we don't know mu, we can't hope to find sigma, because sigma, if you remember back to our calculating standard deviation, comes from the mean. So if we don't know the mean, there really wouldn't be a way for us to know the standard deviation. But in this section, we're just going to assume that we do, and that either we know it from a previous study or just that it's given to us in the problem. Some other terms we want to get familiar with that'll lead us into what we want to accomplish in this section. The first idea is called an interval estimate. If we go out into the population, collect a sample, and calculate the mean of that sample, obviously that mean is most likely not equal to the population value, and you would probably agree with that. What instead we might choose to do, and that we're going to look at doing in this section, instead of relying on a single point, we're going to use that point to create a range of values that we believe our population parameter, that mu that we're after, lies within. So we call that an interval estimate. Instead of just relying on a single point, we rely on a range of values. that interval estimate and how wide we make it, etc., is based on the level of confidence we choose. So we call that our level of confidence. And literally, the level of confidence is the degree of certainty that our interval estimate contains the population parameter. This level of confidence is not something that we just throw out there. It's actually very calculable and is based on some of the concepts we learned in the last section. Putting those two things together, we have what's called a confidence interval. So remember that a confidence interval is taking those two ideas, a level of confidence and an interval estimate, and putting them together. It's an interval estimate that's associated with a certain level of confidence. To create my interval, we have to calculate something called the margin of error. The margin of error is the largest possible distance from the point estimate, which remember is our x bar, it's our sample from the population, that a confidence interval will occur. So it's the largest possible distance we would move away from the point estimate in which a confidence interval occurs. Symbolically, we use E to represent the margin of error. Sometimes you're going to see ME used in that respect as well. And basically, an interval is made up of a lower boundary and an upper boundary. And once we have decided on the margin of error, we can subtract the margin of error from my x bar to get my lower endpoint, and add the margin of error to x bar to get my upper endpoint. Once we have found that margin of error, we have basically created a confidence interval. In estimating the mean of a population mu, a sample will be taken, x bar, and a given margin of error will be calculated, E, for a given confidence level. Keep in mind that we have not looked at how to find E. We're just looking at if it's given to us at this point. Once we have that value, we're estimating the mu of the population by adding E to the point estimate and subtracting E from the point estimate. We can also write this as an interval, lower boundary, comma, upper boundary. Very simple idea. Here's a bit of a picture and an example of what we're talking about here and where we get this quote-unquote level of confidence, etc. So let's just say that we've taken 20 different samples from a population and that the means are calculated. We also calculate the margin of error to be 2.4, and the confidence intervals are created with the 95% level of confidence. Now this particular example is based on height data. So all 20 different samples that we took of 20 produced a different mean, a different x bar. But regardless of what our sample produced, we used the same margin of error for each part here. In other words, we subtracted 2.4 from 44.45 and added it as well, so got lower and upper boundaries for each. Here we can see that the true mean of the population was 44, and that stays consistent throughout all my samples. That's not going to change. And all the green dots here represent our point estimates. We see that our point estimates, our x bars, are kind of all over the place, but they're basically kind of centered around the mean, 44. The intervals, however, if we extend to the left and to the right, we can see that within these intervals, almost all of these samples, once we created the intervals, contained the true population parameter, with one exception. This one right here. This particular mean came out really high, and that would just mean that the people within that sample of 20 that we picked happen to have a higher than average height per person, and so that pushed our mean to the right, which does happen with means as we've discussed in the past. And even once we created our confidence interval from that, the population values still fell outside. However, 19 out of 20 is not bad, and in fact, if we take 19 divided by 20, that is a 95% probability that my population mean was captured within most of my intervals. This 95% that we get is not just something we make up. It's something that's very quantitative. And in fact, it's based in the idea of the normal curve. Remember that in the central limit theorem, as long as we took samples of at least 30 from our population, it didn't matter how our original data was distributed, that we know the behavior of the sampling distribution is normal. In other words, those X bars put together and done many, many times, we put them into a histogram and fill out into a normal distribution approximately. Given that information, we can use the z-curve to help us come up with values that we believe will capture a certain percent of the population. If we wish to capture the middlemost 80% of the population, our level of confidence then is 80. And the z-value that goes with it is 1.28. You can confirm this on your calculator by taking the leftover area from 80. If 80 is in the middle, that leaves 20% total in both tails. Each tail, however, contains 10%. So if we go invert norm 0.1, comma 0, comma 1, this tells you that the z-value, the z-values, I should say, that would mark off 80% of our data is at positive and negative 1.28. 85 is 1.44. 90 is 1.645. 95 is positive and negative 1.96. 98 is 2.33. And I believe on this is actually a very rounded value. It actually would be 2.326. And then the last one for a 99% level of confidence, that's 2.576. Again, the idea here is that we have a normal curve, and we have these two values, the positive and negative of these values, marking off this percent under the normal curve. So it's a lot like the empirical rule that we discussed earlier, except these are very specific values, and the empirical rule simply used rounded off values as a general rule. For example, for 2 standard deviations, supposedly under the empirical rule, that captured 95%. In reality, 1.96, not 2, captures exactly 95% under the standard normal curve. We use 2 just because it's easier to use, and generally with the empirical rule, we're just trying to get estimations. Once we know the critical value for z, which is tied directly to the level of confidence I pick, we can calculate the margin of error, E. And simply, this is how we do it. We take a given z-value for our level of confidence that we've chosen. We multiply by the standard error, which is sigma divided by the square root of n. Standard error is the error if we take into consideration that we're taking samples from our population. So basically, it's z times the standard deviation over the square root of n. Once we have the margin of error, we create our confidence interval by adding and subtracting it to our point estimate x bar. So let's look at an example. We're going to create a 95% confidence interval given that a sample of size 64 comes out to have a mean of 52. And also, we know the population standard deviation sigma to be 5.5. Again, this is a little bit unrealistic. However, we're going to operate under these assumptions in this section. So, for a 95% level of confidence, 1.96, negative 1.96 are the two values that mark out 95% of the data under the normal curve. We call this number, the 1.96, our critical value. So in calculating the margin of error, what I want to do is to translate what this would be, what the value would be here on the left, and what the value would be on the right. That would mark out 95% of the data under this parameter of having a mean of 52 and a standard deviation of 5.5. So first we find our margin of error. We take the 1.96, our critical value for the given level of confidence. We multiply it by 5.5 over the square root of 64, and this comes out to be 1.35. Adding and subtracting it, we create our confidence interval. 52 minus 1.35, 52 plus 1.35, which gives us 50 to 65, 50.65, all the way up to 53.35. So, if this was our point estimate, what we took from our sample, we would then infer that in the general population, the mean is somewhere between 50.65 and 53.35 with a 95% level of confidence. Here's another way to write that out. It's important that you understand how to write out a conclusion properly in these sections. We state our confidence level. That's always important. The reader needs to know what bar you used, how high you set the bar there. We can be 95% confident that our population mean is less than 53.35 and greater than 50.65. Here's another example for you to work and to try doing this on your own. Pause the video at this point and see if you can construct a 99% confidence interval for the number of toys purchased per child per year. The answer here for our confidence interval is 5.27 all the way up to 5.52. We would say that we can be 99% confident that the number of toys purchased per child per year is between 5.27 and 5.52. Another example, biologists studying the healing of skin wounds measured the rate at which new cells closed a razor cut made in the skin of an anesthetized newt. Here are data from 18 newts measured in micrometers, millionths of a meter per hour. Remember that these 18 newts represent our sample. Now we want to create a 95% confidence interval with this data, assuming that the population standard deviation is known from past studies to be 8 micrometers per hour. So really what we need to know is what is the average rate, millionths of a meter per hour, at which our newt's skin is healing. We can use our calculators to find this point estimate, and then use 8 in the 95% to create a confidence interval. Pause the video. Here's your answer. You should get 21.97 all the way up to 29.57. I want to point out also here another way that confidence intervals, or another, at least a notation that is sometimes used, especially on WOMAT. In this notation, we took the point estimate of 25.67, and we just write it as plus and minus 3.7, which is our margin of error. And of course, when we carry this out, when we actually add 3.7 to it, we get our upper boundary, and we subtract, we get our lower boundary. But the main idea here is one of the forms that they have you do on some of your homework problems says margin of error, point estimate, or X bar, plus and minus ME, which is your margin of error. Sometimes they have you report your answer in this way. So there's 3 basic ways that it's reported. Number 1 is this way, margin or point estimate plus or minus a margin of error. Secondly, an interval notation, where we have a lower boundary, comma, upper boundary, which should always be followed and surrounded by parentheses. And then, of course, we have the last one, which is a trilinear inequality, where we have our point, our value that we're trying to estimate here in the middle, mu. On either side is a less than symbol, and then we have our lower boundary on the left, upper boundary on the right. All three are legitimate ways to represent a confidence interval. Most of the time, you're either going to use a trilinear inequality or a interval notation in your reporting. That is it for 11.1 and Module 10.